Great. So we are going to move to another subject, which is closely related to topological quantum computing, which is surface codes, and which introduce a very important and fascinating field, which is quantum error correction. So today, Utkarsh Azad is with us from Azad Quantum Technologies and International Institute of Information Technology in India, and he will give us talk about surface code design for asymmetric error channels. Utkarsh, please, floor is yours. Thank you.
Thank you so much. Thank you for the introduction. And this work was done as part of the QIntern program. And it was done with like me, Alexandra, Shilpa, Rijul, and we were mentored by Ritajit and Deboshmita. They are at ISI Kolkata. So in this work, we try to design kind of surface code design for quantum computers that have like biased noise. And that what I mean by that is something that I would be explaining throughout my talk. So first thing that I think most of you would have realized after listening to so many talks today and yesterday as well is that one of the major challenges that we face in doing quantum computation is building the hardware that could actually combat the errors that come up during its like working. So what we have seen is like the logical error rate that is required versus the current best physical error rates that we can obtain. There's a like a large order of magnitudes difference between those two. And in order to make like do some kind of a useful computation, we will need to like approach those levels, and until unless we do that, like we wouldn't be able to do like very useful or impactful work using what quantum computers can enable us to do. And these errors basically are like I could segregate them into three particular types. These could be decoherence errors. These could be like interaction and coupling to the environment, thermal noise. Like these get entangled with the outside environment, so thermal noise can occur. Decoherence can occur. These could be continuous control errors because like your experimental equipments would not always be accurate. There would be some precision errors somewhere missing. So there would be these kind of coherent errors, and then there would be spam errors, which are the like the state preparation and measurement errors. So you wouldn't be able to like always prepare the correct initial state. Your register might not always be all zero, and while doing the measurement, there could be like your if your measurement time scales for your hardware is not like in comparison with the like the relaxation time of your qubits, then there could be measurement errors that your qubit would have actually like gone from 1 to 0 by the time you were trying to measure it. So what quantum error codes, like the key takeaway from this slide is like the quantum error codes is basically like it's a clever way of encoding your quantum information to protect against these kind of errors. Like these kind of errors will always exist, but what we have to like do is like to come up with a strategy that we can actually like protect against or correct for these errors. So a brief like a review I would like to give, like I had to like decide like between how to introduce the topic in like in this short time and also present you the results. So a brief overview would be, so in the classical side we have these bit flip errors and eraser errors that your bit can either get flipped 0 and 1, or it could get erased, everything goes back to 0. But on the classical side it's very easy that you can just do a copy of all the bits and do a majority voting in some sense. But there is a big problem when it like when we try to replicate this kind of scheme into quantum world, because there are no go theorems like no cloning theorem that doesn't allow you to first to copy your qubit, so you wouldn't be able to do that. Second is, how would you then do this kind of a majority voting? And another thing that separates these two is like there is existence of a new kind of error known as these phase flip errors, and then there are these coherent rotations. These could be due to some like extraneous Pauli error around your qubit, something or like, or there could be some incoherent errors due to thermalization. So what quantum error correction tries to do is it tries to like distribute your state into like many physical qubits, and we use something called as stabilizers to deal with these errors. And I would be explaining stabilizers like later on in the talk, but what you can understand from stabilizer right now is like stabilizer is something that would basically allow you to like tackle this problem of back action, in some sense that the measurement that you are trying to do on your like trying to do for getting the uh, error that would have occurred in your system, but you don't want to disturb the actual state that you are trying to encode. So otherwise because in quantum we will try to like, as long as you don't measure the state, it would be protected. As soon as you measure the state, it would like collapse to either of the eigenstates of your operator or observable. So by using stabilizers, what we try to do is we try to prevent this kind of back action, and we will see how we do that. And another important like thing that comes into play when we are discussing about error correction is this architecture trade-off with like the overhead that is introduced by like implementing the whole error correction scheme, that should be actually like lesser than the like we should be able to get much better recovery or reduction in error correction in errors when we try to implement that scheme. So there's always a trade-off between how much reduction happens and how much overhead that particular code will give you. So the components are very simple. These are basic three components. You can imagine all error correction codes to be something like this. Like you can a module will basically track the quantum errors. For our purpose, we call them as stabilizers and syndrome measurements. Second thing would be to like now I have my like kind of results from these measurements. Now I have to like identify what actually happened. So we have like these decoding algorithms which basically takes those results and try to decode what could have like what errors could have actually possible. One of the examples of these decoding algorithms is this minimum weight perfect matching. And lastly, what we do is like now we have the identified those errors. Now we will correct for those errors. So this is basically the overall idea. And the all of this is to like do some like go from this error correction threshold to something to do like to go towards a regime where we could be able to do something useful for our with our quantum computers. Now to introduce the idea of stabilizers, what you can think of stabilizers as, you can think them of as an like an operator, which basically in some sense your error code will basically encode your uh, state into a particular format. And what this operator basically does is whenever you try to measure uh, that encoded state with this operator, it will always send encoded state will be basically the eigenstate of this operator. So it will get stabilized in some sense, and then you can basically perform this multi-qubit measurement without actually collapsing individual qubit. Your overall qubit state will always like collapse to one of the used eigenstate, and that would basically help you like now you can like check whether the error that happened commutes with the eigenstate, the operator u, and depending upon that, whichever eigenvalue you get, you can like uh, kind of uh, identify error from there. So if I could give you a very simple example, if I had my operator u as just the x gate, like an x Pauli X. So that would actually help you to identify Z errors. And vice versa, if I had a Z stabilizer, when my U is Z, it would help me to identify X errors. And like the key takeaway that you can take from here is something like this, that once you measure the stabilizers, what you get is these syndromes, like syndrome measurements that I was referring to in the last slide. So upon measurement of these of a encoded state with respect to this operator u, you get these syndrome measurements, and these syndrome measurements will give you the information that you require about the the error that had occurred, about the correction that you would then have to do. So stabilizer basically project your errors with certain probability that depends upon your input state, and you kind of repeat it in like a iterative cyclic manner, so that you keep on like stabilizing your input state into one of the eigenstate and keep on correcting the errors. So I would like give you an example in the next slide. Yeah, and one of the main things now, if I have like this kind of setup, how would I build a like a logical qubit out of it? So the idea of building a logical qubit is that I would have, say, n data qubits. N data qubits is like the number of physical qubits I would have, and then I would have, say, m stabilizers. Then the dimension of my complete thing would be 2 raised to the power n minus m. And for building a like a qubit, this dimension has to be 2. So n minus m should be 1. So I would for building a logical qubit, first thing is that you require is to like have a correct number of stabilizers. So you, for n data qubits, you need to have n minus 1 stabilizers, and your whole of the information will be distributed among these n data qubits. So overall, these collective n data qubits plus n plus m stabilizers will form your complete logical qubit. Then you will so once you have this 2 dimension, you will have your basis ready for representing a logical qubit, and then you will have to identify these logical operators, basically similar to what we have for a single qubit, uh, Pauli X, Pauli Y, Pauli Z. So simply you need to have these logical operators for bit flip and parity flip, ZL and XL. And these like the stabilizers basically in some sense give you the constraints of your error correction code. So the constraint for your logical operators are that these have to commute with stabilizers. So these have to have like simultaneous eigenstates. And and they also need to follow Pauli algebra. So ZL and XL in itself need to anti-commute, so that because we know Pauli gates would like anti-commute with each other. So these two criteria have to be fulfilled in order to build a logical qubit out of this kind of setup. Now, what surface codes now now we have discussed kind of in general what error correction is and how we build a kind of a logical qubit. Now, what is a surface code? So surface code is something like what I do is like I make a 2-dimensional lattice. I define it on a 2-dimensional lattice, which have like nearest neighbor coupling, which in general is like I won't say the easiest, but more practically viable solution when we try to build hardware. And what we try to do is we have these data qubits and these measure qubits. Measure qubits will basically give you those like syndromes, and using those measure qubits you will define your stabilizers in some sense. And these would be for surface code, these would be in these checkered patterns that you can see on the left side figure. So if you see these white circles, these white circles are your data qubits, and these black circles are basically your measurement qubits. Now what you are trying to do is the XXX, you can see these 444, like each data qubit is surrounded by 4 measure qubits, and each of these basically define one kind of stabilizer. So so X stabilizer would basically allow you to identify whether a poly Z error occurred on your phase error occurred on your data qubit, and similarly the Z stabilizer, like this kind of stabilizer, if you can see my cursor, would I help you identify whether poly X error occurred on your data qubit. So we kind of do these kind of and these measurements are actually done in like a specific fashion, like A, B, C, D. So you start from A, then you start from then B, then C, then D. And once you do this kind of measurement, you get a syndrome, which will basically get you either +1 or -1, depending upon whether the error occurred or not. If it is +1, then no error occurred. If it is -1, then error actually occurred. Then similarly for X stabilizer as well. So you perform this in an iterative cyclic manner for each like each individual data qubits and like measurement qubit. You get the result, you try to then identify the errors and correct for this. So yeah, so but there is a can we improve upon this kind of setup? So what we try to do is, like, instead of dealing with this rectangular surface, we look at it in a from a rotated angle. We rotate a surface by 45 degree, and we see we can actually build something like this, which and this is known as this rotated surface codes. So what it helps in doing is, it still follows that nearest neighbor topology that we had, but it will now it reduces the number of overall qubits that you would require to, in some sense, to encode your uh, logical qubit using all the qubits that you would, data qubits plus measurement qubits. And in general, the if you're this kind of normal surface code would require d square, sorry, n square qubits. Then this would require n plus 1 square by 2. Like, there's a significant reduction. That's what I want to say. And then there is something known as distance of a surface code. So distance basically describes the amount of errors that surface code can actually correct for. So in general, surface code with distance d can actually correct for d minus 1 by 2 errors. So if you look at these figures at the left side, on left bottom side of your screen, so these are rotated surface code with distance 3 and 5. So basically they can correct for 3 minus 1 by 2, that's 1 Pauli X and Pauli Z errors, and 5 minus 1 by 2, that's 2. So 2 Pauli X Pauli Z errors. And then you will have your similar stabilizers that we had, but these are now kind of rotated, and because we were looking at this from 45-degree angle. So you will have your X stabilizers now in black faces, and your Z stabilizers would be in white faces. And these in your logical Pauli operators XL and ZL will be just these lines, uh, uh, like continuous these kind of data qubits, continuous data qubits on your surface code. And these could, you can have multiple Pauli X and Pauli logical operators, as long as these follow that particular rule that they commute with all the stabilizers that exist. So something like this could have been possible. This, instead of going here, this would have gone this side and then continued this side. So even that kind of that would have also been a valid Pauli operator. So yeah, now what you do is basically you try to for each stabilizer you will perform a measurement, and you will get a syndrome, and based on those syndromes you will now try to identify what kind of error would have happened. So for doing that, what we try to do is we kind of try to do some kind of we get these syndromes, then we only take a look, we only consider the syndromes which has value of -1, since -1 represents that some error occurred in the data qubits that is connected to those particulars, that is connected to that particular stabilizer. And then we have a boundary, because it's rotated, so we complete the whole square with these dummy nodes. And then we try to connect these nodes, that connect these nodes with -1 values. And the way we try to connect them is in sense that if I gave a particular value to each connection, then it would have minimum overall weight for the complete connection. So I can describe this by an example. If you look at the bottom side of the screen, imagine you had a surface code like this, like a distance 3 surface code. Then what you and these two, basically there was an error on data qubit 1 and data qubit 9. So you will get -1 values on this stabilizer and this stabilizer. So your syndromes are -1 here. So now you have made these dummy boundary nodes. Now what you have to do is you need to either connect these boundary nodes, these syndrome nodes with boundary or within themselves. Now, depending upon which has the least weight would be your output of your minimum weight perfect matching algorithm. So when you build this graph node edge kind of structure, you will see this as like if I connect it to like individually, I connect them to boundary, then it would be 1 1. Then the overall weight would be 2. But if I connect them to to each other, then the minimum weight would be 1, and that would what be the output. This output will not always be correct. So you see that the prediction in this case would be that the error actually occurred on fifth qubit, which is not true because the error actually occurred in the first and the ninth qubit. But this is like the general sense on how we like try to identify like errors in this kind of scenario. Then there's this idea of I will like fairly quickly suggest that this idea of pseudo thresholds and error rate thresholds. So first thing is that for a particular physical error rate, as you grow, like for smaller physical error rates, your logical error rates will be small until a particular like value for as you like increase your d, but there is kind of an inversion that occurs after a particular threshold rate where you will actually like your logical error rate will actually start to rise as you increase your distance. So this inversion point is known as the like the threshold, and the pseudo threshold is basically the kind of the point where this error correction will lead you to a more secure logical. Basically, your physical error rates would be um, more than your logical error rates. So the whole idea now to design an asymmetric surface code is that in general, what we have seen from actual hardware implementation is there's like a discrepancy in the number of errors that occur. In general, we have more amount of phase flips than parities. So we need to like have kind of a surface code that is not symmetric in that sense. It actually has like biasness towards uh, uh, making like solving more phase flip errors than. So what we do is we kind of build a like a asymmetric surface code which has like a distance like a different distance in x and for z stabilizer. So it will basically this kind of surface code will basically correct for more z errors and less x errors. Now I
Sorry to
would just
interrupt
go.
Utkarsh, but can you
Yeah,
please wrap up, please? Thank you.
yeah. Just giving within 5 minutes I will run. Yeah. So the first result is basically that for correcting parity and phase errors, we basically try to plot the pseudo thresholds, and what we see is that the symmetric surface codes, which would be just say 3 3 and 5 5, for parity errors they would outperform your asymmetric surface code because they can correct for more x errors. But for phase errors, you will see there's a significant increase in the like the pseudo threshold value for your asymmetric surface code. So this is and another reason that parity this there is a reduction in what asymmetric surface code can do is because since you now increase your number of qubits but you still have like lesser number of x stabilizers, so the total combination of how logical x errors can actually come out to play will increase and the number of stabilizers are decreasing, so you won't be able to correct for all of them. The second thing that we tried to look was in some sense was the like how much how asymmetry influences the performance of your asymmetric surface code. So as we increase the asymmetry, we see that the asymmetric surface codes is like asymmetry in the noise. We see your asymmetric surface code will perform much better than your symmetric surface codes. And final result is that so what we try to do is we try to increase asymmetry up to infinity, and we try to like plot different for different distances. What we see is that for when there's a in the symmetric regime, which is this one regime, the symmetric surface codes perform much better. But as you go into this symmetry, intermediate symmetry regime, for less number of qubits, you get more than double the pseudo threshold values. And as you keep on increasing this asymmetry, you kind of plateau out these threshold rates that you can get. And similar trend is kind of observed with the threshold values as well, that as you increase the asymmetry in the noise, you kind of keep on increasing your threshold values and you kind of then plateau out. So
Utkarsh, can
the
you conclude? Okay, thank you.
yeah, just a conclusion that asymmetric surface good, we are trading off the capability to correct for parity errors in order to correct for more phase errors. This could be vice versa as well. And the asymmetry in the error channel, as it increases, we are able to correct more logical errors with fewer physical qubits than by using asymmetric surface codes. And as the asymmetry increases for your surface code, you can get much better pseudo threshold values as long as your noise is biased. And yeah.
Thank you very much, Utkarsh. Very nice talk, very nice topic. So given that Utkarsh consumed all the time dedicated to Q&A for his talk, I will suggest that any questions could be asked on Discord. So let me take one single question, but please try to answer that very quickly, Utkarsh. Google recently showed the reduction in error with distance 5 surface code. Do you think this trend will continue with increasing distance in asymmetric case? Very quickly, Utkarsh, please.
I think so, yes, it would be. And in general, even Google's hardware has this biasness. So that's what industry is trying, like industry and academia are both trying to go towards, like making these kind of biased error correction codes.